Okay, so I welcome you all, and today we will just proceed those commutation relations, and I think we'll start with the same component of linear momentum. Say we'll take on px cap and px cap. Right? So how we'll do it, we will write down this commutation as px cap, and then minus px cap, and again you will have px cap. So you can see it by symmetry yourself. You can see that you're going to get 0 out of here. So you'll be using an eigenfunction, say psi, acting on both sides. So I'll be using the operators for momentum. What you will have is, you will have minus IH bar dou by dou x, and again minus IH bar dou by dou x. And then the same story will go on here, minus IH bar dou by dou x minus IH bar dou by dou x, close it and multiply it by psi. And we can see this minus IH bar, this is 2 times, okay? So outside you will have minus IH bar whole square. And inside you will be left with dou 2 psi by dou x2 minus dou 2 psi by dou x2. This will be the result, okay? So these 2 terms will cancel, so you'll get 0, and you realize immediately that the linear momentum along the same coordinate, they exactly commute with each other. You can exactly calculate them. The nature does not put any constraint in calculating the two linear momenta along the same coordinate. Is this clear? Okay. Now let's go on with a different component. So px cap, and then I will take py cap. Let's take this commutation and see whether they commute or they do not commute. So what we will do is we will get here px cap, py cap, then minus, you will have py cap and px cap, right? Okay, so we can operate the right hand side with a state vector psi and a state vector psi in the left hand side. Once we make the calculations, we can remove these eigenfunctions. So what's going to happen here? I think minus IH bar whole square will be out, right? Okay, so then inside you'll be left with dou by dou x, then dou psi by dou y. Am I right? Minus dou by dou y, and then dou psi by dou x. That should be clear. Okay, so what do we expect now is we can understand what will be the result. So this is whole square. Now this I can write as dou 2 psi by dou x and dou y minus dou 2 psi by dou y and dou x. Right? And we understand from the properties of partial derivatives, what we understand? We understand that if you have dou psi by dou x dou y, this must be equal to dou psi by dou y and dou x. So immediately you can realize what's going to happen here. Immediately you can cancel the 2 and the result will be 0. So you will obtain the commutation between px cap and py cap will be equal to 0. So I can generalize it like Pi and Pj. I think I can use this equal to 0 whether I is equal to j or I is not equal to j. So there is no problem in calculating the momenta, the linear momenta of a particle along two different coordinates at the same point of time. I can calculate its linear momentum along x and along y at the same point of time. Right? Okay? So this is another realization of these commutation relations. So what next we'll look for is I have already shared that video with you on angular momentum. Have you seen that? We have calculated certain commutation relations between position and angular momentum. Okay, so that we have done. And similarly, if I think about this, Lx and Lx, the angular momentum versus angular momentum, you will find this is equal to Ly is equal to Lz is equal to, these are commutation relations equal to 0. They are exactly commuting with each other, and we understand now what commute means. And if you will go with this Lx, Ly, what you will get here IH bar Lz. Okay, you can do it, okay, you can work on it. And similarly, if I go with Ly, Lz, this will give me IH bar Lx. Similarly, Lz, Lx will give me IH bar Ly. Right? And if you reverse the commutation, if you reverse, you can memorize it using that circle. Lx, Ly, and Lz. Okay, you can do that. Okay, you can do that. So here, obviously, if you change it to Ly and Lx, here your result will be minus times IH Lz. So this is how you can find these results when you will try to obtain the commutation relations between the different components of angular momentum. So what we realize at this point is that the angular momentum on the same coordinate can be exactly measured because their commutations are 0. But when you go into the framework of different coordinates, then the outcome is different. Okay? So Lx and Ly, they don't commute. Ly and Lz, they don't commute. Clear? Is this clear? Okay. Now, let's go with another important property, that is Lx and L. Okay? So Lx is a component of angular momentum along x, and L is the total angular momentum. Okay? So what is this L basically? I can write down this as Lx, comma, Lx plus Ly plus Lz. Okay, we know from the property of commutators, what we know, we can write down this as Lx, comma, Ly, Lx, comma, Lx, yeah, plus Lx, comma, Ly, plus Lx, comma, Lz. Alright, so this way, know this is equal to 0. Okay, Lx and y will give us what? It will give us IH bar Lz plus Lx Lz. So it's going anti-clockwise, so it will be minus IH bar Ly. Clear? So I think you can do better than me. So what we will have common here is I, H bar can be out, and inside you'll be left with LZ minus LY. So this is giving you the commutation between what? LX and L. Fine? Right? Are you getting it? Okay. So similarly, I think there is no problem in finding the commutation between LY and L, LZ and L. Okay, now let's go with another important commutation, and that is LX and L square. Right? Now let's see how they commute. What's their commutation? Now, if you talk about this angular momentum, it's your angular momentum in terms of Cartesian coordinates. So it will have three components. And if you write down this L square, what is the magnitude of this L square? It is Lx square plus Ly square plus Lz square, right? You remember that Cartesian coordinates vector r, x, y, and z. The magnitude of r square will be what? X square plus y square plus z square. So I can do that, so I can write down here. So I have Lx, and then I will have Lx square plus Ly square plus, and then you will have Lz square, right? Okay, using the property of commutators, I can write down this as Lx, comma, Lx square plus Lx, comma, Ly square, okay, plus Lx, comma, Lz square. Okay, right? Okay, what kind of commutation I would like to use here? Do you remember something like this? The commutation between A, comma, BC. This is equal to the commutation of A, comma, B times C plus B will be out, and inside you will have A, comma, C. Clear? So A, B commutation, then you multiply it by C plus B as it's the commutation of A and C. And we would like to use this result in resolving those brackets, right? So what we will write down? You tell me I may do it wrong. So what will be the first thing? Yeah, it is Lx. So you will have Lx, comma, Lx, then outside you will have Lx. Then again the same thing will be here, Lx, comma, Lx, and then you will have Lx. No, here it will be Lx. It has to be in the start in this case, right? So it will be Lx, and then you will have Lx, comma, Lx. Okay? Now tell me about the second, plus. What is the second one? That is Lx and Ly square. Now I will have Lx, comma, Ly, outside will be Ly. Plus Ly I will start with, then you will have Lx and Ly. Am I right? I don't know whether I'm doing it right or wrong. You can do it later on, but let us see how we reach out to some results. Okay, then this is gone, okay? The third one is what? What will be there? Plus. Yeah? Lx, Lz. Then times Lz plus Lz, Lx, and Lz. Am I right? Fine? Okay, that's clear. Now you can see this thing is gone because Lx commute. Okay, this thing is also gone because Lx commute. So both of these terms will lead us to 0. This will lead us to 0 and this will lead us to 0. Now here we have to go with some results. So this is Lx and Ly. What I will get here? Come on. I will get I, H bar, L, Z. Okay? Then you have Ly. This thing has happened. Okay, then plus Ly, I, H bar, LZ. Okay?
Minus.
These two terms have gone. Now here it is coming back from,
Minus.
so this is minus IH bar, LY and LZ.
Plus.
Okay. So minus again, okay? IH, yeah, LZ, LY. I think you have done it, okay? So there will be cancellations. All of these terms will cancel. So what does it mean? It means that the x component of the angular momentum commute with L squared. So this is how we calculate it. So what does it mean? It means Lx and L squared is equal to Ly and L squared is equal to Lz and L squared is equal to 0. So these two quantities, these two operators exactly commute with each other, right? Okay, so this is it. Now, if I think about doing some algebra here, suppose I have a commutator between the commutator of A and B, comma, B and A commutator, right? What will be the result of this problem? Now A and B, they are the Hermitian operators, okay? And what you have, I'm not putting the cap, you understand they are operators, okay? So what you have an overall commutator, and within the commutator you have a commutation between A and B, and then the commutation between B and A. Do you predict what will be the result of this problem? Yeah, you're right. So I think you can do it yourself. Huh? So all you have to do is, you will use this property. The commutator of A and B is minus times the commutator of B and A. This is how you will try to resolve some of the more important problems. They will be useful in solving some good problems, right? So anything else? So, any queries? So with this, I would like to thank you all. So let's stop it here. Have a nice time.